Hi, and welcome back to our chemistry flipped classroom. And today we're continuing our conversation about solutions, and we're talking about how we express concentration. So we're going to learn some different ways to calculate concentration, and we're going to talk about relative concentrations. So we're going to have several different ways numerically to express concentration, as well as just kind of more broadly. So let's talk about relative concentration. So these terms don't have a specific meaning numerically. They're really just relative to the solution itself. So we talk about a saturated solution, and a saturated solution is a solution in which there is as much solute dissolved in the solution as could possibly be dissolved. If you tried to add any more, it wouldn't dissolve. It would just sit there and not dissolve. So a saturated solution is one where the solvent is holding as much solute as it is possible for it to have. An unsaturated solution just means that you could put some more in there and it would still dissolve. So that's an unsaturated solution. It's just the opposite of saturated. Doesn't mean that there's a tiny amount. It just means that it is not completely saturated. It could hold more. A supersaturated solution is one where you've actually sort of tricked the solvent into dissolving more solute than should theoretically be possible at that temperature. And the way that this is usually done is that a solution is heated and solvent and solute is added until it's saturated. And then the solution is allowed to cool. And if the solution isn't disturbed, it will actually stay supersaturated. So it's actually holding more solute than should technically be possible. If that solution is disturbed, if you bump it, if you add a crystal, if a little piece of dust or hair falls in, then some of that solute is going to crystallize out and it's not going to be supersaturated anymore. It's just going to be saturated. Then we have a dilute solution. Again, no absolute numerical value to attach to this. It just means that it's not very concentrated. There's some solute in there, but not a lot. A concentrated solution has kind of a lot of solvent in there, a solute in there, but not saturated necessarily. So these are very vague terms. They're used a lot. We talk about a concentrated acid solution or a dilute acid solution. We do talk about saturated, and there is a numeric value attached to saturated, but it's different for every substance. So sodium chloride has a different saturation point than calcium chloride. So this being chemistry, we like to be able to assign numbers. So we have numeric ways of expressing concentration. One of these you've already used, and that's molarity or moles per liter, and we'll come back to that. We're also going to learn today about mass percent, about parts per million and parts per billion, as well as molality. So sometimes we have really low concentrations. We certainly hope that if we have arsenic, it's in very low concentrations. We tend to use things like parts per million for very low concentrations so that it's easier to express a number that we can wrap our heads around, even though it's a very low concentration. So that's when we would use parts per million. We use them a lot in environmental science. You'll see them used occasionally on the news. So tend to be things that are very low concentrations. The one we use the most in the chemistry classroom is molarity. And molarity is just the ratio of moles of solute to liters of solution. So you already know this one. We've been using this one in stoichiometry. So molarity is usually abbreviated as a capital letter M with a line under it. You'll sometimes see it as an italicized capital letter M. But it's important that it's that capital letter M and that you either underline it or italicize it. It's hard to tell italics when they're written. So when it's written, it usually is underlined. So it's moles of solute per liter of solution. Sometimes molarity is not the best concentration expression to use because volume is temperature dependent. And so that volume of solution can vary with temperature, which means that molarity can vary with temperature. So if we want a concentration expression that is not temperature dependent, we tend to use molality. Sounds very similar to molarity, one letter different. but molality is moles of solute per kilogram of solvent. So notice now that we have solvent, not solution, and we're per kilogram, not per liter. And since neither moles nor mass change with temperature, molality is not temperature dependent. So when we're calculating things like colligative properties, how much salt decreases the freezing point of a solvent or how much it increases the boiling point of a solvent, then we tend to use molality. So molality and molarity. Molality is also abbreviated with an M, but now a lowercase m, again underlined. So molarity is uppercase M underlined, molality is lowercase m underlined. Okay, mass percent is one that we use fairly often. You'll see this a lot in commercial applications like hydrogen peroxide or isopropyl alcohol. And mass percent is just the grams of solute per gram of solution. Now notice that we're back to having solution, not solvent. So it's grams of solute per gram of solution. And so we express that as a percent. So we need to multiply it by 100 to get 2%. It's unitless because we have grams over grams. They're going to cancel out and we just have the percent. Okay. Then we have parts per million, and parts per million, like mass percent, it's a ratio of mass units of solute to mass units of solution multiplied by a million, or 10 to the 6th. As I said at the beginning, parts per million tends to be used for very low concentrations. Often it's used to measure pollutants in water or in air. Grams of solute per gram of solution times a million. So we use parts per million. We also use parts per billion. This is for really, really low numbers. So for parts per billion, we're going to use the mass of the substance, the solute in solution, divided by the total mass of the solution times 10 to the 9th, so times a billion. So that's parts per billion. Okay, so these are pretty simple and straightforward. We'll talk about this simplifying assumption that we're going to make. So when we are calculating solutions, we frequently make the simplifying assumption that 1 milliliter of water is equal to a gram of water, which is true at certain temperatures, but not true all the time. But again, close enough. That means that 1,000 milliliters of water is equal to 1,000 grams, or a liter equals 1,000 grams. So we're going to assume that solutions with water as the solvent have the same density as pure water. So 1 milliliter equals 1 gram. Now, is that actually true? Not really, but it's going to be close enough for our purposes. Okay, so I'll leave you with this problem. We're going to calculate the molarity of a solution prepared by dissolving 1.56 grams of gaseous hydrogen chloride into enough water to make 26.8 milliliters of solution. So notice that it's not telling us exactly how much water we're using. We just know that the final volume of the solution is 26.8 milliliters. So before we can calculate molarity, because molarity is moles per liter of solution, we need to convert our grams of hydrogen chloride into moles of hydrogen chloride. And then we need to divide that by the 26.8 milliliters. But since it's per liter, we want to convert the 26.8 milliliters to liters. So we've got a couple of steps here. Let's see if we can get this figured out. So we have 1.56 grams of 1.56 grams of hydrogen chloride, and we are going to divide that hydrogen chloride, 1.56 grams of hydrogen chloride. We're going to divide that by the 36.46 grams of hydrogen chloride per 1 mole in order to find our number of moles. And then we're going to divide that by the 0.02 0.68 liters of solution. Okay, and that's going to be our molarity. So as always, I look forward to answering your questions in class, and I will see you soon.